Welcome everyone. Welcome to the IEEE CAS workshop. Sorry. Yes. Hello everyone. Welcome to the IEEE CAS workshop. Today we are streaming two more researchers about video processors, and the second talk is about circuit yield analysis and optimization. Don't forget to register for free on our website in the description. Subscribe to the channel, like the video, and enjoy this amazing workshop. Now the session chair will introduce the first speaker. Professor Gustavo Sanches, please. Welcome.
Good morning, everyone. We will have the first presentation of Yibo Fan from Fudan University in China. He will talk about an open source video codec IP core and his short bio. He is a full professor with the College of Microelectronics, Fudan University. His research interests include image processing, video coding, machine learning, and associated VLSI architecture and open source IP core design. He founded the first open source IC design website in China and released the first open source 8265 ATVC video encoder IP core and H8264 AVC video encoder IP core. So he sent here a video of his presentation because he was not capable of being here at this time. So let's start his presentation.
Hello everyone, my name is Fan Yibo, and I came from Microelectronics School of Fudan University in China. Today, I wanted to share you the topic XK265, an open source video codec IP core. Firstly, I wanted to introduce about my lab in Fudan, and also the SK Silicons, which is startup foundations to support the open source IP core. Secondly, I want to discuss the difference between software and hardware codec designs. Thirdly, I want to introduce our work, SK265 architecture, that is an agile hardware design for multi-scenario codec optimizations. And then I would like to introduce two enterprise edition IP core. The X1 is for silicons, which is low cost and has best PPA performance and has good RD performance IP core. And the second IP core is K1, which is for FPGA. And the K1 is a 4K H.265 soft IP cores for 4K video in FPGA. And last, I wanted to introduce our open source roadmap. Okay, let's start from introduction part. Here is my lab. My lab name is Video and Image Processor Laboratory in Fudan University, and which can call as VIP lab for short. And my lab, the research field covers 4 parts. The first part is video compression processor, and we did research on the many coding standard from H.264 and 265 and 266, and also the AVS3 and the SWAC2 And these two standard is Chinese domain coding standard, and also we do research on everyone. The second part is image processing processor. In this part, we do the research on ISP and also the image compression process like the JPEG, Lepton, HEIF, WebP, DSC, and VDCAM. The third part is mainly focused on algorithm level research. It is the learning-based ISP and the video codec, and we do the AI-assisted ISP and also AI-assisted codec. The fourth part is heterogeneous computing system modeling. We use Gen5 and based Gen5 to do the system simulation model for SoC system. Here's the introduction of SK Silicon. SK Silicon is a startup foundation which focuses on video and image hardware IP core development and open source. And we have already released 2 open source video IP cores. And also we developed enterprise editions, which is for domain-specific video codec IP core. It includes 2 IPs. The first is X1. X1 is for silicon, for the low cost and high RD coding efficiency applications like IPC camera, which can be used in civilian systems. And second IP core is K1, which is for FPGA. And the K1 has a low LUT cost and high video quality. Our vision is to provide the golden reference video codec IP design to industry and also to the whole societies. We use the 3 ways to do the output. The first is the open source output. So everyone can download our IP core with RTO source code is free. And they also can get our FPGA demo source code. And the people can do the quick prototype based on the open source IP cores. The second way is we can output the IP core, which is similar as the IP vendor's product. We call it as enterprise editions. And we can provide the better PPA and the better RD efficiency. And we can do more custom design options. The third way is RMD power output. We call it as a golden reference for industries. And so we can open our algorithm documents, the C model source code, the RTO source code, and also the people and the students to industries. So in this way, we can help the company to build their R&D power in codec designs. Okay, and next, I want to discuss the difference between hardware and software video codec designs. There are many software codecs in China. You can see this figure. It shows the MSU video coding competition in 2020. It becomes the Chinese company battlefield. And you can see the first place is Aurora encoder, which comes from Vision and Vision Neural. It's a Chinese startup companies. The second one is BBC. BBC is from ByteDance. And then it's QAV1. It's QAV1 from the iQIYI. The V265 is from Tencent. And the S265 is from Alibaba. And the BD265 is from Baidu. And the XCCZM is from Beagle. It's also a Chinese startup companies. And before 2020, Huawei has HW265, which is the first place, win the first place award before 2020. And besides this commercial software codec, there are numerous open source projects for the software codec, like the X264 and the X265, and also the AOM. In the other part, a hardware codec solution depends on IC company, and there are few open source IP cores. And for chip level solutions, you need to use the chip designed by IC companies, and most of them is from US. And currently, the most popular codec IC is from the Intel and NVIDIA, and they embedded the codec uh, hardware accelerator in their CPU and GPU. And for the chip designs, you need to buy the commercial IP from the IP vendors. And this IP vendor can be from the ARM, from the Imaginations, or the chip media. And in China, there are only one IP vendor, is Valley Silicons. Otherwise, you need to do the R&D by yourself. And for the FPGA designs, people also need to buy the commercial IP. Otherwise, they can use the FPGA chip with embedded hardware accelerator. But the dumb part is you need to pay the high price, and the platform is dependent the specific FPGA chip. And there are very few open source resource in this area. And what are the difference between software and hardware codec? And for the software, everything is processed in serial executions. So the CPU needed to can do the each part of the codec. So there's no data dependencies. You can write your algorithm very freely. But for the hardware, the things is different. For hardware, everything is executed in parallel, and the hardware pipelines. There are many data dependencies in hardware pipelines. So the designer need to handle all of these data dependencies. And also, the designer needs to manually control I/O read and write from the DDR. So the hardware design is much more difficult than the software designs. And for hardware design, usually we need to first to develop the C models to evaluate the coding efficiency, and to make the pipeline be no data dependencies. For hardware designs, there are two approaches. The first is use hardware coprocessor. You can design a coprocessor with CPU and use some specific instructions to accelerate the video coding process. And you can see for Intel, there are media SDKs, and for NVIDIA, there are NVENC. And another approach is use hardware IP core to do the IC chip designs. And so you can for the IP core, there are hard core and the soft cores. The hard core is used for chip designs, and the soft core is used for the FPGA designs. And so you can see for hardware design, the IP core design is very important, because currently most of the chip they use the IP core. They will embedded the hardware IP core in their chip. So why we need the hardware video codec? Because the hardware video codec can achieve much more power and price benefit. And also, it can achieve the real time and low latency. And this software codec cannot process the video in real times, and the latency also very high. And the hardware video codec can support 4K and 8K with very high IL bandwidth. And currently, maybe all of the 4K and 8K real-time video system, they need to use the hardware video codec. So next, I wanted to introduce the SK265 hardware architecture. And because based on our knowledge, the different applications may require different codec IP cores. So the IP core also need different features for different applications. For mobile phones, it need very high image qualities, but the power should be very low, and also the compression ratio can be low. And for the IPC, IP camera, because it is used for the civilian systems, so the compression ratio should be very high, and the image quality should be middle. And for the IoT, Internet of Things, it need a very ultra low cost and ultra low power, and the image quality also can be low. And for the FPV, first-person view controls, it need the ultra low latencies, and for the video quality can be the middle to lows, and it should support the multi-channel video streamings. And for the cloud transcodings, it need the high RD cost, high RD coding efficiency, and also high qualities, and it also needed to support multiple channel parallel processing. Now for the set-top box, it needed to do the decoding for multi-format, so it needed to support the different coding standards, and the video quality should be high, and the compression ratio can be middle to high. And here shows our SK265, the design target and the features. For the algorithms, and for algorithm and standards, we are trying to develop extensible architecture. It means that it can be extended to support different video coding standards and the unique hardware architecture. And also, this architecture can embed different algorithms. The second is flexible hardware architectures for power, area, and feature customizations. We provide the many configurable designs. For example, the PE cores, pipeline stages, and search algorithms, and also the CU, PU, TU, the partition switches, and all of these features can be configured, and because we needed to make balance between power, area, quality, and RD efficiency. The third one is we are trying to design a unified pipeline for encoder, decoder, and also support the multi-channel coding. The unified pipeline, which support also can be configured to the encoder only or decoder only, or the encoder and the decoder both to support, and also can support multi-channel configurations. The CTU level channel switching is a key features for the low latency multi-channel designs. And also, we like to provide many parameters for user configurations. It can support hundreds of coding control parameters for users to cover different video coding scenario. And the configurations like the RD ROI, the RD preference, the CU, PU size options, also the rate control options, and also the audio control options. Here we show the XK265 unified CDC codec architecture. The architecture includes many modules used in IP cores. The RMD module is intra-rich modernization module, and the FTH is fetch module to load the original pixels from the main memories. The IME, FME is integer and the fractional motion estimations, and also include the RDO. And the rake is a reconstruction loop. The DBF SAO is a filter, in loop filter used in codec. And the ED is an inch-p decoder. EC is an inch-p encoder. The DMP is dumper modules to dump the reconstructed pixels to main memory. And all of these modules can be configured, and you can include all of the modules to be codec support I and P frame encoding or decoding. And also you can remove part of the modules to get the specific encoder, maybe the only I frame encoder or P frame encoder, or just I frame decoder or the P frame decoders. The pipeline stage can be also extended to more pipeline stage number. You can see in this slides, we extended, here we show encoder instance case, and we called it as a K1 IP core. And the K1 extended the architecture to 7 pipeline stages. So you can see all of the modules is the same as the previous slides showed, but the pipeline stage is extended from 5 stages to 7 stages. And this K1 is used for FPGA implementation. Now, because the FPGA has more the frequency of the FPGA can't be very high, so we needed to use more stages to improve the parallel processing. And here shows a decoder instance case. It also include the 7 pipeline stages. So these 2 cases shows that based on our baseline architecture, we can configure the modules used in the IP core, and also we can configure the pipeline stages used in IP cores. And so in this way, we can meet the different application scenario and to do the custom designs for different applications. And for each modules, we provide many configurable options, and all of these options can be classified to 2 kinds. The first is static options. The static option means that when you configure the options, the hardware circuit, the real hardware circuit, will be changed based on these options. The dynamic options means that when the hardware is fixed, you can configure some register and to do the process step adjustment and to make the IP core be configurable. So the static option will affect the hardware cost, and the dynamic options will not affect the hardware cost. Now, for the RMD modules, we provide the static options like the processing element PE, PE core number, and the prediction mode number, like the DC or planar. You can disable it or enable it. And for the dynamic options for RMD, we provide the search PU size and also the search inch mode. which can be used to balance the quality and the performance of the encoder. And we here we provide the configure register for examples. Here we just list part of the registers. And for the RME, for static options, we provide the set tree PE size. You can configure it. It can balance the area with the performance, and also the search patterns, and also the PU size, supported PU size. It also used to adjust the area and the versus quality. For dynamic options, we can configure the search pattern. You can use different faster search method, and this search pattern will affect the quality versus performance. And here we show the IME configure way. First, you can configure the search path, how the path configured to do the motion estimations. And the second is the search windows, the shape of the search window. You can adjust to the different video sequence. And for the fractional motion estimations, for the static options we provided is the P number and also the PE size. And it is used to balance the area and versus performance. And also we provided the P latency cycles. It is used to balance the area versus timing of the P processing elements. For the dynamic options, we provided the search P size and the search points. It is used to balance the quality versus performance. For the audio part, the static option is P size and the search P size, and also the search P size. The P size is used to balance area and the performance, and the search P size is used to balance the quality and the performance. For the dynamic options, you can adjust the intra-test mode number, and also you can force DC or planar or disable DC and planar. And the force intrachroma mode equal to 36. And also we provide many switches for the merge, skip, and I block in P frame, and also other coefficients which can be used to content adaptive decision policy. And for the CABC, here we designed a high parallel CABC VLSI designs, and which can processing multiple beams in one clock cycle. And here, the total BPCC it can be to 4.37. It means that we can processing more than 4 beams per clock cycle. And next, I will introduce the enterprise edition IPs and their performance evaluation results. First is X1, which is designed for silicon. Here is the key features of X1. X1 currently, our X1, it has been successfully used by IC companies. They use the X1 IP core in their IPC chip. Our X1 here support the HEVC main profiles, and the format is YUV420, and the bit depth is 8 bit. It support I frame and P frame, and also so it support the encoder and the decoder. And the CTU size is 32 by 32. because we wanted to make the X1 be low cost, so we didn't use the 16/4 CPU. We just used the 32/32 to reduce the on-chip memories and also reduce the logic. And below 32/32, we support all kind of size CU, PU, and TU. And for rate control, we support the CBR and the VBR. The frame level and also the frame level rate control by software, the CTU level rate control by hardware. And for fetch part, because fetch is used to read or write the reference frames. So here we support the reference frame compression. And the RMD, we support all 13.5-inch prediction mode. The IME, the search range is 32 in hands and 64 in wise. It is also support configurable search pattern. For the FME, is 1/4 quarter subpixel interpolations, and also it support the configurable search center. And for the RDO, we use the true RDO based on reconstruction loop to do the RDO. And it also support the CABAC debugging and the SAO and other features like the ROI configuration, and also we support iframe, MP, and also skip and merge. This IP core has been successfully implemented in Global Foundry 22 nanometer, and the frequency, the highest frequency can support 800 megahertz. The throughput it can support 4K at 13 FPS with the audio level high, and 4K at 16 FPS with audio level medium. The area is 2.2 square millimeter. Here we provide the RD comparison with the commercial IP core. Table 1 shows the bit rate compare with the chipped media and the valid silicon. Under the rate control is on, and here the anchor is X265 media. You can see the for the I and P frame compressions, the overall the average bit rate, the bit rate bit rate is similar as a commercial IP core vendor. Yeah, and the rate mismatch. Here we get the smallest rate mismatch compared to other two IP vendors' IP core. And the table 2 shows the constant QP tester. The anchor is also X265 media. Here our model outperforms other two IP cores in iframe compressions. So you can see compared to the chipped media, we achieved 5% better than the chipped media and 10% better than the valid silicon. And the P frame is similar as the chipped media, but worse than valid silicon because we use the smaller CTU size. So the P frame we will not as good as valid silicon. And for the FPGA, we designed another IP core. We call it as K1. For K1, the key features is similar as the X1, but the here we use the main difference is we use a very small CTU. We just use a 16 by 16 CTU because the most of the FPGA the hardware resource is very limited. So in FPGA, the 32 by 32 CPU is very hard to integrate the whole encoder in FPGA. And if we wanted to design a 32 by 32 CPU, we also need a very high price FPGA. So because we want to implement our IP core in some very low cost FPGA, so here we reduce the CPU size to 16 by 16. And for the performance, in FPGA implementations, the frequency cannot be very high. So here we in FPGA we just achieved 140 megahertz frequency. So, but we also support the 4K at 13 fps with audio level media. So if you want to get a much more RD coding efficiency, when configured to audio level high, the performance can be achieved 100 HD at 16 fps. The area is about 170K LUT. Here we show the video quality comparisons for the FPGA implementations. All of the test data is under the constant QP test. The anchor is X264 and media. And for the iframe, you can see from this table that for the iframe, our K1 IP core is better than X264. And for the P frames, the K1 baseline is similar as X264, very fast configuration. And but the baseline is a very tiny IP cores. We removed many key modules in K1 baseline. And if we use the K1 baseline plus a DB and SAO, the RD performance can be similar as X264 medium. And if we add more coding tools, the RD performance can be similar as X264, very slow. And here we show our K1 demo systems. We use the 3 displays and the 2 FPGA board. And firstly, we can download our circuit from the host PC to these 2 FPGA by USB tab. And we will input the video from HDMI board, which the video source can be provided by PC2. And the first FPGA is do the H.265 encoder, and the encoded bit streams can be transmitted by Ethernet, and the other FPGA board will receive the bit stream to do the decoder. Then the decoded video can be output. The decoded can output the decoded video to another HDMI board and displayed in another display. Now here is our demos. You can see the video. Okay. In the last part is our open source plan. For our IP cores, we firstly released our first versions in 2017. And this version is very primary stage versions. We just implemented our algorithms into hardware. So we support all function modules like IME, FME, inter, DCT, deblocking, SAO, CABAC. And the CPU size is supported 16.4 by 16.4 and only support I frame and P frame. There's no rate control and also no audio part in this release. So there's only encoder core without AXI interface. And in 2019, we released another versions. We call it as version 2.0. In this version, we improved hardware performance and integrate more coding tools and features supported. And here we propose a new pipeline architecture, and we added many tester. We do the many tester in these versions and make the code quality to improve the coding qualities. And here we also support iframe and pframe, and support iblock in pframes, and also support the merge and skip. But these two parts is not fully tested. And here we integrated a simple audio engines in IP cores. There are also no rate control supported in this open source release, and only encoder cores without AXI interface. And here we provided C models for testing and compare the model and the RTO results. And in this year, we plan to release another fundamental versions. We aimed to it can be really used in FPGA with low, especially for low cost FPGA. And here, our target is first is for FPGA. Second is for the low latencies. It can be used in some real-time processing video system. The third is ultra low cost. Because the FPGA hardware resource very limited, we need a very tiny IP cores which can be really used in FPGA. And finally, we will provide the whole XI interface and also the demo system source code. And here we show our future plans, and also another part work in our group, and especially for XK silicons. First part is Codec IP, and currently we do the open source. We have two projects open source. First is X2 264, and another is 265 IP cores. And for the enterprise editions, we have X1 and for silicon, and K1 for FPGA. And then currently we are working on X2, which is IP core supported two standard. And another project we just we have already did more than 1 year is ISP IP, and in the end of this year we will to release XK ISP. It's also open source ISP. Here this work we are cooperated with Alibaba. Yeah. The third part is the DSA MPUs. Because we are doing many research on especially for algorithm level research for the AI codec and the AI ISP, and we are trying to to design a DSA NPU, a domain-specific architecture NPUs. This NPU is especially designed for the AI-assisted codec and the AI-assisted ISPs. The target application of our work is the chip design and FPGA design, and also the hardware accelerator used in cloud. Here, I received a question from the chair. His question is, are there plans or ongoing work in your group to continue developing IPs for the next generation video coding standard as VVC or AV1s? My answer is yes, of course. We are working on VVC IP core based on our CDC architectures. Yeah. And also, we are planning to design a unified architecture to support the AVC, HEVC, VVC, AV1, AVS3s can be supported to many other coding standards. And we call it as VPU, Video Processing Unit. And also, currently, some IP vendor they are named their video coding IP as VPU. And so in my lab, we also trying to design a unified architecture for VPU to support the different coding standard, encoder or decoder or codec, especially for the cloud transcoding. Yeah. Okay. Thank you for listening. If you have any questions, I will welcome to write email to me. Okay. Okay. Thank you very much. Bye-bye.
So we would like to thank Professor Yibo Fan for his presentation with so many insights for video coding, design, for hardware design. And since he was not capable for being here virtually, he just sent a video. We would invite you to send a mail for him with your questions, so he can help you. Well, thanks again for Professor Yibo Fan.